All right. So with our logarithmic functions, what you have to keep in mind is your logarithmic functions are your inverse of your exponential functions. When you go to find your inverse of your exponential functions, it creates this whole new thing. So they called it logarithmic functions. So to refresh our memory, in order to find the inverse, if you're given a set of points, you simply switch your x and your y. So let's say, for example, we have a table of 1, 2, 2, 4, 3, 8. What would our table for our inverse look like?
2, 1,
yep.
4, 2, 8.
2, 1, 4, 2, 8, 3. So you literally just switch your points around. Switch your x and your y's. Those are the easy ways when you're given your set of points, just switching them like that. If you have a graph and you need to find your inverse, that means you need to reflect it over the line y equals x. So we'll draw a quick little picture here. So there's my graph, my x and my y axes. I'll draw a little exponential graph on there, which is that little curvy guy. So the line y equals x is that diagonal line that goes right through the origin. Has a slope of 1. So when you reflect it over that line y equals x, your graph ends up going over here. So as our exponential graph, my little red graph up there, it had a horizontal asymptote at y equals 0. Remember, it's got this little imaginary line here it can never cross. But when we reflect it over that line y equals x, our horizontal asymptote becomes a vertical one. So our inverse has a vertical asymptote as opposed to a horizontal one. And then does anybody remember how to find your inverse from an equation? Switch your x and y. It's kind of like your points. You switch your x and y, and then you solve for your y. So let's say we had the equation y equals 2 to the x. If I switch my x and y, what's my inverse equation? X equals 2 to the y. Now, as I said, normally with your inverse, we would then solve for y, but do we know any rules that allow us to bring the y out of the exponent spot? I know I certainly don't. So that's why they created the logarithmic function. It allows us to take the y out of the exponent spot, and then you can graph your equation, you can solve your equation, all those other things. It was created to solve more complex math kind of problems. So it's used a lot in chemistry class, it's used a lot in engineering today, and a whole bunch of those more complex problems is when they use it. So let's take a look at our graph. What I want you to do right now is we're going to graph y equals 2 to the x. So using your calculator, I want you to get a table of values. For your x's, I want you to go from -2 to +3. So let's have you go ahead and do that. To graph the inverse. So to graph the inverse, I find the easiest thing is just to take your table of the first one and flip your points. So we're going to have 0.25, -2, 0.5, -1, 1, 0, 2, 1, 4, 2, and 8, 3. So once you flip your points, then go ahead, plot your points, and draw your graph. So now they want us to write the equation for the inverse. So I'm going to start with my original equation, y equals 2 to the x. As we said up above, we need to switch our x and our y. So I get x equals 2 to the y. And then we can't leave it like that. We got to get it into y equals form. So that's when they bring in that word log. So we always take our exponent and we set it equal to. So in this case, our exponent was a y. So y equals log. And then down with the log, you're going to put your base. My base here is a 2. So I put a little subscript 2. It's meant to be smaller. And then you put the other part of your equation there. So our x goes next to it. So that's the way it always goes. This is always your exponent. Down here is your base. And this is what I like to call your answer over there. We'll be practicing with that a lot throughout class today.
So is that what it's written as?
Yep. Y equals log base 2 of x. Okay. So now we're going to graph y equals log base 3 of x, which you can't exactly do that in your calculator. So what you have to do is you have to rewrite as an exponential function and make a table, but you want to fill in your y's first. So what that means is I'm going to take this out of log form. So if you remember, my little number down there, that's my base. My exponent is always on the other side of the equal sign. So I get 3 to the y, and it's going to equal x. But we can't type that into the calculator. What we can type into the calculator is its inverse. We can type in y equals 3 to the x. So let's have you go ahead and do that. So go under your y equals. Yep. Go to your y equals, type in your 3 to the x.
Wait, what? I'm sorry, I was still putting in the graph.
We can't graph this, so we have to type the inverse into the calculator.
Way back up there.
So when you get this into your calculator, though, when you get your table, you just want to flip it, since you want to graph the inverse. We don't want to graph this one. We want to graph the inverse of it. So you just want to flip your table in there. So instead of my x's, I'm going to put them as my y's.
So it's like y equals log 2 of x.
Log base 2 of x. And then our decimals are going to go over here. That's like a 0.11, 0.33, 1, 3, 9, and 27. So you use the 3 to the x to get you your table, and then you just flip your points to get you your log graph that we actually want. So go ahead, plot your points, make your graph. All right, so let's take a look at our graph here. So if you keep in mind what I set up before, this has a vertical asymptote. Our log graphs always have a vertical asymptote. So seeing how that does have a vertical asymptote, that means our domain will never be any of the negative numbers, right? X will always be a positive, so how do we write that for our domain? Say it louder. X is greater than 0. It'll never equal 0 because of the asymptote, but it'll always be greater than 0. So then for our range, can we get every single y value possible? Yep. So our range would be y is an element of the reals. What would our x-intercept be? 1, because that's where it crosses our x-axis. So then our vertical asymptote, as I said, it's this dotted line right here. What would be our equation for that dotted line?
X equals 0.
X equals 0. Because it's a vertical, it's always going to be an x equals. So that's our basic graph there. So let's take a look at the top of the next page. I put a couple of reminders up there for you.
Wait, I'm sorry, you didn't get all of these.
So this one over here is what we call our log form. Y equals log base b to the x. It's the exact same thing as what's written over here on the right, which is our exponential form. And we're going to have to go back and forth between the two because you can't always solve something when it's in log form, but sometimes you can't always solve it in exponential form, so you have to switch it to the log form in order to do so. So we're going to practice going back and forth between our logs and our exponentials. And the other main key thing to keep in mind here, a logarithm means your exponent. Logarithm is a fancy word for your exponent. So keeping that in mind, when you put it into log form, that's why it's always your exponent equals. Because log means exponent, so exponent equals exponent is basically kind of what you're saying up there. All right, so one of the things we have to do is we have to be able to evaluate our logs. So if you're given something like log base 2 of 8, what you want to do is you want to first set it equal to x. We need a variable in there somewhere, so I'm going to set it equal to x to give me one. And now I'm going to take it out of log form. So keeping in mind, here's my base, so I have a base of 2. Your log always equals your exponent, so my exponent is an x, so I have 2 to the x. And then 8 is my answer. So it's 2 to the x equals 8. And now it's just like the equations we were doing before in our last unit. How can we rewrite 8? 2 to the third. So 2 to the x equals 2 to the third. So now what's true about our exponents? Our exponents are equal, so x equals 3. So our next one, I'm going to first set it equal to x because I need my variable. So now I'm going to take it out of log form. What's our base? 4. Our exponent is the x. It always equals your exponent. And then our answer is 16. So 4 to the x equals 16. So again, we got to change our 16. That's equal to what? (16) is 4 squared. So now I have the same base. They're both 4s. So x equals 2. All right, so our third one there, again, I'm going to set that equal to x. So what's our base? Our exponent. And our answer? 1/3. So 3 to the x equals 1/3. Now how can we rewrite 1/3? 3 to the negative 1. Our negative exponent gives us that fraction. So 3 to the x equals 3 to the negative 1. So our answer is negative 1. So our next one, I'm going to set it equal to x first. Do I have a base written? No, I wrote you a little note here. If no base is written, the base is a 10. I could get in a whole little side tangent about why it's a 10. We live in a base 10 number society, blah, blah, blah. But just keep in mind, if there's nothing written, it's a 10. So if you want to, you could go up there and write your base of 10 to help you remember. You don't have to, though. So this would be 10 to the x equals 100. Which 100 is 10 to the what power? 10 to the second. So therefore, x equals 2. Now our next one that's not a typo, that is the ln of 5. When it brings in the ln, that means your base is that letter e we talked about a little bit back in our last unit. ln means it's a base of e. So we would rewrite this as e to the x equals 5. But we really can't do anything else with that because I can't change 5 so that it's e to some exponent. That just doesn't work. So for these ones, we just simply use our calculator. So they want, I already got it typed in there. They want to know the ln of 5, so I'm going to push the ln button, which is over on the left, third from the bottom. And then you put your 5 in there. And then let's round that to 4 numbers after the decimal. So it would be what?
So it would be x equals 1.6.
Oh, nope. We would just have to write 1.6094.
So you
That is the ln of 5.
press ln and then 5.
Mm-hmm. So then for our last one, again, I'm going to set it equal to x. What's our base? So we get 2 to the x equals 5. Now again, can I change a 5 so that it's 2 to some exponent? No, that doesn't happen. So we leave that one like that for now. That's actually something we're going to get into in a couple of days on how to be able to solve that. So this one we're just going to leave as this. Okay, now the little bit tougher part. We're going to rewrite these ones into log form. So we have our exponential form. We're going to rewrite it as log form. So I always start with the exponent first. It's always the exponent equals. So I'm going to start with my x equals. And I'm going to put log. It's base 2, because there was a 2 that my exponent was on. So I make a little 2 there. And then we put our answer, which was 5. So x equals log base 2 of 5. How about for our second one? What's that going to start with? I always recommend starting with your exponent, so we're going to start with z equals. What's our base? Nope. Base is a 4, so it's going to be log base 4. And then we want it of 6, so log base 4 is 6. And then our last one, our exponent is a 5, so I'm going to start with 5 equals. What's our base? 3 of a. So it's 5 equals log base 3 of a. So down here on the bottom, all we are doing is we are taking it from log form and you're going to practice putting it in exponential form. You're not evaluating anything. So I want you to just take a couple minutes, try these 4, see if you can put those in exponential form. Equals a. Now 7's tricky because you guys tend to forget. There's no base written, so what number is it? 10. So this would be 10 squared equals w. So there we go. That's going back and forth between our log form and our exponential form. So let's take a look at our last 4 examples here. So solving basic log problems, what you want to do is you want to put it in exponential form. And then once you put it in exponential form, generally you're able to see what you need to do after that. So looking at number 1, our base is a 5. Exponent is an x. So it's going to equal 1 over 125. So this is like what we were doing for our warm-up. We got to get the same base. So 5 to what power is going to give me 125? The third. And since it's a fraction, I need to rewrite this as 5 to the negative 3 equals my 5 to the x. So then what's our answer end up being? X equals negative 3. So it's kind of like what you were doing with our evaluating, only they already had it set at equal to x for us. Number 2 is just a little bit different. Our base is a 4. What is our exponent? Negative 1/3 equals our x. Now, since it's the number with the exponent, we just have to figure out what that equals. And since it's 1/3, that means we have to take what root of 4? Cube root. Is there a cube root of 4? No, so we need to use our calculator for this one. So let's have you go ahead in your calculator, do 4 to the negative 1/3 power. And we're going to get a decimal.
How many decimal places?
Let's go with 4. Point 6, what?
629.
Nope. Got a round.
So then it'd be 63.
Yep, ends up being 6300. Because the 6 makes the 9 turn into a 10, which makes the next 9 turn into a 10, which makes the 2 turn into a 3. Whole bunch of rounding there. All right, number 3, again, our base is what? 5. Our exponent is 2. And it's going to equal x minus 3. So we'll figure out what is 5 squared. 25. And then what do we do with our 3? We want to add our 3 over so that x is on its own. So we get 28 equals x. So it's not always going to be a change of base. Sometimes you just got to figure out your exponents. So in our last one in our notes, what's our base? 10. It's going to be to what power? Negative 3. And it's going to equal your x. So now this one we can actually figure out, whereas 4 to the negative 1/3 we needed our calculator. Because it's negative, that makes it turn into 1 over 10 to the 3rd. Now our exponent's positive by making that fraction. And what is 10 to the 3rd? 1,000. So it's 1 over 1,000 equals our x.